Hello, Mr. Collier here. This is part 3 of Lab 7B, Conservation of Energy, and in this video I'm going to show you how to do the analysis for the data we've collected. This was the lab where we had the bent track and we had to use this little string here to measure the height of the car at different drop positions. We also measured the mass of the car, and with that we're going to look at the potential energy of the car before you drop it and use that known to predict the kinetic energy when it gets to the bottom. So one of the first things we need to do is use the equations we've been working with in this chapter to figure out how to calculate the speed of the car based on its starting potential energy. Here's the basic idea. We can figure out the potential energy of the car using the formula mass times gravity times height. To do that, we just need to measure the mass of the car. We know gravity, and then we need to measure the height of the car at the different drop positions. Then we're going to say that all of that potential energy we start with will turn into kinetic energy at the bottom of the ramp. So we can set those two values. In other words, we can say mass times gravity times height, potential energy, is equal to 1/2 mv squared, the kinetic energy at the bottom of the ramp. Now we simply need to solve this equation for velocity, and that'll be able to tell us how fast the car should be going when it gets to the bottom of the ramp. So to rearrange this equation to solve for velocity, first I'm going to cancel out the m's because there's mass on both sides, so it doesn't matter what that number is, it's multiplied on both sides. We can get rid of it. Then I'm going to multiply both sides by 2, which will get rid of this 1/2. Now I've got v squared equals 2gh. So then I'm going to simply take a square root. The square root of 2 times g times h equals v. So this will then be the equation we use to predict the speed of the car at different positions. So here we have our data table. We've got a lot of different information going on here. I'm going to walk you through all of it using the data from video number 2 where we collected that data. The initial drop height was 0.13 meters. The mass of the car was 113 grams, so I'm going to convert that, 0.11381, I think actually, kilograms. And with that we can calculate the potential energy. So that would be mass, 0.11381, times gravity, 9.8, times height, which was 0.13 meters, and that's going to give us an initial potential energy of 0.145 joules. Now we're going to figure out the predicted speed at that drop height. So we're going to use the equation I just derived, which is the square root of 2 times g times h is equal to the predicted speed. So square root of 2 times 9.8 times the height, which is 0.13 meters. Type that into a calculator and I'll come up with a predicted speed of 1.60 meters per second. So then we actually ran the car down the ramp and got a time of 0.0067 seconds. To calculate then how fast it was going, we just do 1 centimeter divided by that time, and you get an actual speed of 1.49 centimeters per second. To calculate percent error then, you're simply going to do your predicted speed, 1.60, minus your actual speed, 1.49, and divide it by your actual speed. Now just a reminder, don't forget to put those in parentheses if you're using a calculator. Multiply that by 100 when you're done, and you'll get a percent error. For this one, it happens to be 7.3% error. So to recap so far, we measured the height at different drop positions. We massed the car. We used those to calculate the potential energy. We use the potential energy to predict the speed at the bottom because all that potential turns into kinetic. Then we actually sent the car down the ramp and measured the time. Then we can calculate the speed of the car from that drop position, and finally figure out how close our prediction was to our actual measurement. The last thing to do then is to graph our data. And in this graph, we're going to compare the speed of the car to the initial drop height. The drop height we're going to go in increments every 1, 2, 3, 4, 5. Every fifth block is 0.05 meters, or 5 centimeters. On the y-axis, the speed is going to go every 5 blocks is half of a meter per second, 0.5. The main ideas in this lab are that dropping the car from a higher height gives you a higher initial potential energy, which then converts into greater kinetic energy at the bottom, so the car is going faster. But also, because all of the potential turns into 100% kinetic, we can make predictions about how fast the car will be going at the bottom part of the ramp. That's part of the law of conservation of energy. Good luck.